So we have one of our people from MIT Video Productions today taping this session because we're going to be putting it up on the web because we think that this is such a good session that you may want to refer to it later on in the semester. Also, it'll be available to other TAs at the Institute if they're interested in perfecting this particular craft. And I think that teaching the art of problem solving is a craft. It's not something that all of us know instinctively how to do. In fact, teaching, I think, we don't always know instinctively what to do. Yesterday, after I gave you my story about my miserable first day, and Margie asked you, how many of you thought it was all a setup? Most of you raised your hand. The reality was, I always give that story every year because it's so indicative of how badly your first day can go, even though you think you're really well prepared. Margie, however, had never heard that story, and being a good teacher that she is, she seized on the opportunity to teach you all the things that she wanted you to get out of the session. So that in itself is a great lesson to take away, that sometimes your students will give you this wonderful teaching opportunity that you hadn't planned. So seize it and act on it, and don't be afraid to give it a try. So with that, I am very, very happy to introduce Sanjoy Mahajan. And I'm wearing my glasses today so I can read this time. Sanjoy obtained his PhD in theoretical physics from Caltech in 1998 and has undergraduate degrees in mathematics from Oxford University and in physics from Stanford University. What he says is, due to his wonderful teachers, he became interested in improving science teaching, an interest he followed as a postdoctoral researcher and faculty member in the physics department at the University of Cambridge and as a fellow of Corpus Christi College, Cambridge. His favorite course to teach is the art of approximation in science and engineering, an graduate course for which he is writing a textbook that will be published in print using a free software license. And if you get to know Sanjoy, you'll find that freeware is very, very, very important to him. While at Cambridge, he helped start the African Institute for Mathematical Sciences in Cape Town, South Africa, where he was the first curriculum director and taught the first courses in physics and computer science. There he wrote the free software to automate barcoding and cataloging the 5,000 donated books that started the Institute's library. In an earlier life, he did research in computer game playing, co-authoring a world championship-level Othello program. His interest in science teaching and in how artificial and natural minds work make him a happy member of the Teaching and Learning Laboratory, which he joined in July 2006 as Associate Director for Teaching Initiatives. And the MIT TLL is a terrific resource for all of you. They are there to help you improve your teaching, your leadership skills in the classroom, in research groups. That's their primary focus. These people think about teaching every day. In January 2007, Dr. Mahajan was named a lecturer in MIT's Department of Electrical Engineering and Computer Science. We are very fortunate to have him running this two-day workshop for us. Please join me in welcoming him.
Thank you, Melinda. So they're teaching the art of problem solving. So let me start with the problem. There are 26 sheep and 10 goats on a ship. How old is the captain? So this was one of the questions given to first and second graders in France. What do you think the majority answer was? Yeah, 36. Yeah, so about 85% of the students made an answer, and almost all of them said 36. Did you think, well, that's interesting. What the hell did they say 36? So people wanted to find out, okay, well, what's the reasoning behind it? So they asked the students, oh, okay, well, what was the reason for 36? Very deadpan, not trying to give away the store. And the students, many of them said, oh, well, the captain forgets how old he is, so he puts one more animal on the ship every year so he can always look at them and remember. So they really, really, really wanted to just combine the numbers in the problem. And a similar problem shows that it's actually a very sophisticated form of combining, though it's just combining. So a similar one was there are 125 chickens and 5 ducks on a boat. How old is the captain? And so the students slightly older, most of them said 25. Why 25? Well, so they asked the students that. And they said, oh, well, 125 plus 5, and that's 130, that's too old. 125 minus 5, oh, that's 120, that's also too old. It must be divided. So what you see here is a fundamental problem with how we teach problem solving. Because what's happened is that the problem has no meaning for the students. You say, oh, okay, well, that's a foreign country. That's across the Atlantic. That's France. What about here? So here, similar sets of studies were done. This was with high school students. They were 15-year-olds, about 35,000 of them. They were asked the following question. There are 1,128 soldiers. They have to get to their army base, and they have to be bused there. And there's 36 people who can fit in every bus. How many buses do you need? Now, there are many possible answers to this question. As far as I know, it was at least below 1%. Nobody said 1. Oh, because you can just shuttle the bus back and forth. So let's assume they didn't say 1. And furthermore, most of them did the division correctly. So there's no point us doing the division right now. So I'll just tell you what the division is, and then I'm going to ask you to predict what the students said. So okay, it's 31 1/3. Okay, so take 30 seconds, take a minute, meet one of your neighbors, and try to predict what the students said of the 70% who did the division correctly. What did they write down as their final answer? So this is trying to put yourself in the mind of the student, which is a very valuable skill when you're teaching. So they said many different things, and see if you can predict what the possibilities are and how frequent they chose each one. Okay, so anyone want to volunteer one of the answers? Yeah.
Like most of them would have said 31 1/3.
Okay, so 31 1/3 is one answer. Yeah, so most. Any other answers? 32. Yeah. 31. And indeed, those are actually very good predictions. So this might have been the slight minority. These are all roughly evenly distributed. This was maybe a slight minority. Maybe this was a slight minority, but these were slightly lower than this. So indeed, this was the plurality. But if you went to high school or grade school in America, you know that you're taught not to write that. You're taught this bizarre thing where you write it like that, which is the most ridiculous thing. But that's what I was taught too. 31, remainder 12. So this is actually the way they wrote down this answer. They wrote down 31 R12. Now, this one, of course, that's right, and that's good. This one, it's not right, but at least it shows some level of thought from going from here to there. They said, oh, okay, they thought about what to do with the 1/3, and they concluded incorrectly that it didn't matter. But these people, they clearly didn't even think about that issue at all. They just went from 31 1/3 and said, okay, great, put it down, just like the sheep and the goats. So these were 15-year-olds who had all been sampled across the country, been doing plenty of math for the last basically 11 years. So what happened again is the same problem. The problem didn't mean anything to them. And that's a fundamental problem, so to speak, when you're teaching problem solving. If the problems don't mean anything to the students, they're actually what they're learning instead of the art of problem solving is they're learning the art of pattern matching. And the art of pattern matching is fine as long as you keep giving them more and more patterns to match and more patterns to match. But then what happens is when they graduate, they fall off a very steep cliff, or maybe even before. All of a sudden someone asks them to do a real problem, and they're looking around, oh my God, what equation? Oh, that has a P and a V and a Q. Are there any other equations with P, V, and a Q in it? I don't know. So for example, you'll find students who, even at MIT, if they have a problem where they're given an equation sheet and they have to solve for some velocity v. They'll write down v equals at from the equation sheet, but they'll also write down v equals IR from Ohm's law. Why is that? Well, they both have v in them. Right? So they're figuring you might as well cover your bases. Right? So again, it means nothing, absolutely nothing. So an extreme example of this same phenomenon, this is again from America, is directly problem solving, is word problems. So that's a classic thing you teach in mathematics. I'll talk about why I keep talking about math problems in a second. But word problems of the form, Johnny has 5 apples, Jane gives Johnny 3 apples. Why is it always the woman giving the man the apples? But anyway, that's how they usually are phrased. Johnny has 5 apples, Jane gives Johnny 3 apples. How many apples does Johnny have? 8. Okay, we understand that one. The other variety is Johnny has 5 apples, Jane takes 2 apples from Johnny. How many apples does Johnny have left? Oh, 5 minus 2, 3. Okay, but then the brilliant further question they asked students was, Mr. Jones has 5 apples. Mr. Left gives Mr. Jones 2 apples. How many apples does Mr. Jones have? What do people say? It's hard to imagine that this can actually happen, but this is actually what happens. People say, oh, 5 minus 2 is 3. Now, why do they do that? Oh, because there's a left, Mr. Left. So they see the left in the statement of the problem, and that triggers because there's 2 problems they have to solve. First is, what numbers do I have to combine? Okay, well, there's 2 numbers in the problem. Clearly, I'm going to combine 5 and 2. How do I combine them? Right? Should I divide them, add them, subtract them, multiply them? Well, there's left. Left tells you what you need to do. Says, how many do I have left? Okay, so 5 minus 2 is 3. Right? So this is a fundamental problem of lack of understanding of anything. So and as I said, this is actually very terrible for generalization, for students actually solving real problems in the world that you want them to solve. You'd like them not to depend on you when they leave your classroom. And that can be taught. So the way I'm going to try to show you how one possible way of teaching that, what we're going to do is we're actually going to do several problems together, and we're going to make careful note of the techniques we use and the ways of teaching it so that you can use the same in your own classroom. So now, why all these mathematics problems? Well, the answer is that I could give particular chemistry problems or physics problems or, say, other harder math problems, but the value of using elementary math problems is that the content of the problem everyone understands. You don't have to think about it. It's all completely obvious. And the words are all defined. You have to just think, how are you going to use the concepts together? And you can focus on the problem-solving techniques. So that's why we're going to use a few problems that don't require any calculus or any fancy math at all, so we can focus on the problem-solving techniques. Okay, so what I'm going to do is I'm going to first give you problem 1. So before I do that, let me just note a bit of chalkboard technique, which will help you a lot whenever you go into the classroom, which is as soon as you come into the classroom, the first thing you should do is put board number 2 down. Now, let me show you why that is. So I'll demonstrate on this board. So this should be your first board that you write on. And then down comes board 2. And then when you're done with board 2, you start writing on board 3. So the point is that the students always have a whole board of context before something gets covered up. So there you can see board 2 and the start of board 3. Whereas normally what happens, suppose the blackboards have been cleaned the night before, all the boards are up. Right? So now what happens is, I'll demonstrate that over here. Let's say I came in rushed to class, and I just put down my notes. I'm like, oh my God. And I just got to the board. I didn't remember to do my magic with the chalkboards, and I start writing over here, board 1. And I'm happily going along. I'm thinking about the equations I'm doing, about whether people are paying attention, who's reading the paper back there, who has their laptop on. I'm all nervous about all those issues. I'm thinking. Then I get here, I'm like, oh my God, I need to write some more. Now what do I do? So I have half finished some derivation over here, let's say, and now I want to continue it. Okay, this one's easy to pull down. Oh no. Now I've covered up the other half of the derivation. So then I've gone through this thought process many times, like, oh yeah, I'll solve that. I won't use that board. I'll use this board. Of course, it has the same problem. But when you're in the middle of teaching, your intelligence on those matters drops significantly, is one way to put it. So what you want to do is you want to help yourself be as intelligent as possible by pre-preparing everything. So that's why you pre-prepare it in that order, with this board first, and then you can write on that board. Okay, so let me practice what I preach. I'm going to write on board number 1 first. Okay, so problem 1. Okay, so the first problem is to find the sum of the first odd n odd numbers. Okay, so now the best way for you to practice problem-solving techniques is to try it yourself. So find a neighbor or two, see if you can find the sum, but then take note of whatever methods you used. And that's what we're going to focus on. We're going to focus slightly on the answer, but also on the methods that you used to find it. You don't, I mean, there's techniques you can use to get it exactly right away, you know, with an elephant gun. But focus on your exploration, what you do, how you come to whatever answer you come to. Or even if you don't come to an answer, what you're trying and thinking about. Okay, so find a neighbor or two. Make sure you introduce yourself. You'll be working with each other for the rest of the year. So it's good to make friends now. You can help each other, give good examples to each other. If you have any questions, raise your hand and I'll come over. Oh, yeah.
What's up?
And if you don't have anyone right next to you, you can always turn around and join somebody. Hi. You can join them or we can chat a bit. Go ahead. Yeah. No, minus the sum of the even numbers.
Minus the sum of the even numbers?
That's
so
right.
It's like written like that, so I just sum this ones and like decrease from this one.
You might be able to simplify it. Yeah, and check with the people around you as well. They might have a different expression, and then you guys can argue about. Oh, you're trying a few examples. Not a bad idea. So do you have a conjecture?
Z squared.
Can you prove it?
So you have n, and then the other number is just a relationship in sum, because what you're trying to relate is n and the sum. So if n is 1, the only odd number you have is 1.
So you have a few examples that are consistent with it. Can you prove it? So if one of the examples had not worked, you would have disproved it. But can you make sure that it would work for every single example? So if you have a conjecture, see if you can prove it. The reason I ask is there's all kinds of things that, for example, no one knows if they're true, but they know they're true for up to 1 trillion. So the one is, do you know the Goldbach conjecture? So that's the one that says every odd number is a sum of every even number is a sum of 2 primes. And up to as trillion is maybe higher than that now. No one's found a counterexample. and everyone's pretty sure it's true, but you would win the Nobel Prize in math for proving it. So, I mean, I'm not claiming that people win the Nobel Prize in math for proving that one, but it's the same idea, is that just because you have a whole bunch of examples, that's a great thing, and that's where you come up with theorems. But then when you want to prove them, you're going to do something else too. So both are good, guessing and proving.
No, I mean, like, if you, this is,
Who has a conjecture but not a proof? Okay, let me just give you a short disquisition on conjecture and proof and why both are good things, and then I'll let you argue for a bit more. So the reason is conjecture is great, and coming up with a possible candidate for that is a great thing. And then the question is, well, is that enough? And the answer is no, not quite, because you do want to prove your conjecture. And why is that? Well, there's lots of statements in mathematics which people are pretty sure of, and they verified for a lot of cases, but they just don't know if they're true. So the one that is most striking in that is the Goldbach conjecture, which says that every even number is a sum of two primes. I'm pretty sure that's what it says. But it's been verified up to 1 trillion, or maybe even more. But nobody has any idea of how you prove it. And you probably win the Nobel Prize in math for proving it. It's called the Fields Medal. So now I'm not saying this is at the level of the Nobel Prize in math, but the idea is you want to see if you have a conjecture and you're pretty convinced it's right, see if you can find some way of being sure that it's right for every single case. Okay, so take another 30 seconds, and we'll start discussing. Okay, so let me reassemble everyone for a short discussion on your approaches and your conjectures or ideas. Okay, so what way of going about it did you think about? Yeah.
I wrote the sum of the first n odd numbers as the sum of all of the first n numbers minus the sum of the first n even numbers.
Okay, so I'll just write that as shorthand. The sum of the odds is the sum of all numbers minus the sum of the evens.
And the sum of the evens can be written as the sum of all numbers, as twice the sum of all numbers up to n minus 2, n minus 1 over 2.
Okay, so this is twice the sum of all up to n over 2. Oh, maybe it's n minus 1 over 2. Yeah, I guess it depends if n is odd or even. So we'll have to worry about that slightly. But the basic idea is that you can sum the evens because you divide each one by 2 and you get all the numbers just halfway up. Okay, so that's method. So approach 1, let's call this. Okay, other approaches. A table. Okay, so you make a table. Okay, so n and the sum of the odds. Okay, so n is, let's say 1. 1. N is 4, because that's 1 plus 3. N is 3, and that's 1 plus 3 plus 5. Even I can do that. How far did your table go? 4, okay, so 4, you add 7. Not a trillion, no, that's okay. So you go up to 7, so you get 16. Okay, so you made a table. Did anyone else make a table? Yeah, table, a few tables. Okay, so let me ask someone else. Once you made the table, what do you then do? Look for a pattern, okay. So I'll summarize both these methods in a second. So you make a table and look for a pattern. Okay, so the pattern is n squared, right? Okay, so we have several techniques. I'm going to put the techniques over here. So first, in this problem, this approach, you actually replace it with something else that you know how to do. Right? So this, you're not sure how to do it, but you know how to do the sum of all the numbers. Let's say that's just n times n plus 1 over 2. You know that one. But if you didn't know it, then this method wouldn't work as well for you. But if you do know that, you can use that knowledge to solve this and to solve this by reducing it to that, and then combine it to solve your new thing. So one technique is to reduce to already solved cases. There's a story of the mathematician who joins the fire brigade. And he's doing great. There's a couple fires. He goes out with them. He's in training. He goes out with them. He plans all the ways of putting the water into the house and taking the fire down until manageable level. Everyone can enter the house. He gets medals for what an excellent fireman he is. And then there's a call from someone who has their cat stuck up in a tree. So what does he do? Well, he sets the house on fire. Right now, why would he do that? And then, the fire trucks come and they put out the fire, and while they're there, they get the cat out of the tree. He says, "Well, why did you do that?" He said, "Oh, well, we already know how to do that. Get the fire brigade here, put everything out. I was just reducing it to an already solved case." Right? So that's the extreme case of it, but it is actually a very powerful technique, reducing to already solved cases. Another one is to make a table, or I'll give you a general name for that, which is to look for extreme cases and simple cases. Okay, so simple cases can lead to a pattern or a guess. So basically, you're looking for simple cases and then look for a pattern. Another way of saying that is making a guess. Guessing. So combining simple cases and guessing gives you educated guessing. Okay, other approaches. Yeah.
The nth odd number I wrote as 2n minus 1.
Okay, so let me just use one of these techniques again. So whenever I hear something like that, I think, as a programmer, I think, oh, is it 2n minus 1 or is it 2n plus 1? I'm pretty sure it's one of those two. So how are we going to check? Simple case, yeah, we'll put in n equals 1 and we'll just make sure we get it right. So if n equals 1, we're saying the first odd number is 2 times 1 minus 1, which is 1. Great. Okay, so it's 2n minus 1. Okay, so now I'm happy.
Okay. And now I write the sum as s equals 1 plus 3 plus 5 dot 2n minus 1.
Right, so the sum is 1 plus 3 plus plus 2n minus 1. Yep.
Once again, I write the sum as 2n minus 1 plus 2n minus 3 dot 1.
Okay.
I add these two sums with the corresponding terms, so I get n into 2n minus 1.
Okay, so you add up all of these guys.
Sorry, I get 2 into sum equals n into 2n.
N times 2n?
Yeah, n into 2n.
Okay, so because here there's a 2n when you add these up. There's a 2n minus 3 plus 3, which is a 2n. And there's 2n minus, well, there's a 5 here, which cancels that. So you get a 2n, all the way. So how many of these 2n's are there? There's n of them, right? So this whole thing is equal to n times 2n.
And that is equals to 2 into sum, so you get n squared.
Right, which is twice times the sum, because we added 2 of them up. So that means the sum is equal to n squared. Okay, so now, what technique would you say, if you had to name this technique, what would you say this one is? Besides magic. So the purpose of this whole session is to demystify magic. These things seem magical at first, but they're actually not. You can give them names. So spend 30 seconds and see if you could come up with 1 or 2 words to describe this method. The reason being is that those 1 or 2 words you can use again and again and again in other problems. So talk to your neighbor. See if you can come up with 1 or 2 words that we can put as number 4. Okay, so any words, just shout out that you think I could use to name this. Yep.
Like reduced to already solved cases? It seems to be not so uncommon method in math.
That's true. So you're right. So you're reducing to an already solved case because you do know how to do this sum. So you're right. You're using this one, but you need one more. So you also need one more thing to tell you how to get to this case. You know, when you did this and said, well, it's the same as that. Yeah, you're expressing the same thing multiple ways. So what's that? So for example, this wood block, which we're going to use later, looks the same this way, right? It has a symmetry. So that's actually the name of the method. Yeah, as well as what you say, reducing to already solved cases. And you're using that together with symmetry. And as a chemist, you should be very appreciative of symmetry. That's one of the most powerful techniques, right? If you know the Polya-Burnside counting theorem for counting, which you can use to count isomers, for example, CH5, sorry, not CH5, C4, H5, Cl5. And you want to count the number of isomers of that. Right? So you actually, the way you do it is by looking at all the symmetries of it. And then you apply the so-called Polya-Burnside counting theorem. So symmetry is very, very powerful. Here, you've actually used it to express the same thing in two different ways, and then you combine them, and you get something that you know how to do. Right? So it's symmetry with a little bit of magic and reducing to already solved cases. But by naming the symmetry, you've actually not destroyed the magic, but you've actually seen where it comes from. So there's an old example of this, which is from the mathematician Gauss. It was said that when he was 3, he was pesting his teacher so much. In fact, the whole class was bothering the teacher so much that the teacher said, all right, you guys, add up the numbers from 1 to 100. Expecting that they'd be at it for the next 15, 20 minutes, 30 minutes apiece. And up comes Gauss after 2 minutes, said, oh, I know the sum. It's 50,100. Yeah, I think that's what it is. And the teacher said, well, how did you do it? Exactly this. Instead of doing 1 plus 3, you just do 1 plus 2 plus 3 all the way up to here, and you do n plus n minus 1 all the way across, and you add again, and you have the same symmetry argument. So it's a really, really, really powerful technique, symmetry. Okay, so now let's try, any questions about any of these techniques? Okay, let's try one more problem, let's see, which one should we do next? Okay, so let's do a semi-math, semi-chemistry problem. So I'll leave this board here, and I'll write techniques over here, and I'll use these boards for the problems. Okay, so the next problem is, what is methane, CH4? What's the bond angle? Okay, so what I'm going to show you is a way of approaching that problem that uses some of these techniques as well as one new technique. Okay, now you could just remember it. Who happens to... And what you'll find is after you do it by a couple different ways, you will remember it. I happen to actually remember the number. Who else happens to remember the number? Yeah, oh, wow, great. I'm in a chemistry audience. Okay, so now the question is, where does that number come from? Right, so if you happen to remember it, you can tell me if I've remembered it wrong, but I think it's that, right? Okay, so let's see if there's any way we could actually come to this conclusion without doing lots of miserable mathematics. So here is your methane. Right, and you want this angle. Or any of the angles, they're all the same. Well, the first thing is I start to wonder, well, this is kind of hard, right? It's hard if you want to try to figure it out. You may have to use dot products and vectors and God knows what. But what's hard just thinking about it is that it's in 3 dimensions, right? So you have to visualize this 3-dimensional angle. 3-dimensional angles are very tricky. For example, if I asked you what's the angle between the faces of a tetrahedron in 3 dimensions? It's not easy because it's sort of, you can look at the projection, that one's easy, but actually in 3 space it's not so easy. So what I'm going to do is I'm going to apply this technique, simple cases, and look at some simpler problems, simpler versions of the same problem. So a simpler version is this one. In 2D, so this is now fake carbon, right? This is not carbon as you know it, and it has 3 H's and it's in a plane. So what's this bond angle? And so that one, oh, I know that one, right? That's 120. So in 2D, theta equals 120 degrees. Okay, well, let me start to make a table. So this is D for the number of dimensions, and we'll try to work out theta. So in 3D, we have no idea. 2D, it's 120. Well, it's kind of hard to guess from one data point, right? So we're going to do a fair amount of the other technique over here, which is guessing. But even guessing needs something to start the engine, right? You can't just run it on vapor. So 1 point, not really enough, because you could say, well, it's always 120. But that seems a bit implausible, right? But you can check that. You can say, okay, well, how do we check it? We've got to generate another data point. So what data point could I generate? 1D, right? You could do 4D, but 4D is even harder. So why are you doing 1D? There's a name for that technique. Why? So you are using simple cases, but if you have to do, or particular cases, but if you're trying to decide between 1D and 4D, and you say, well, I better do 1D, what are you being? Lazy, right? So lazy is good. So we're going to put that down as one of the techniques. Be lazy. Don't make your life any harder than it has to be. So let's do 1D. So in 1D, that's just this. It's now some, well, this is, let's call it CO2. That's actually a legitimate molecule, unlike that fake guy over there. So CO2, the bond angle is 180 degrees. And we're probably pushing our luck if we try to go to 0 dimensions. But let's just be happy with the 2 data points we have. Okay, so now we can try to guess what's going to happen in 3D. You can say, well, there's lots of patterns, right? You can say 180, 120, lots of things. Could be 60, right? It's dropping by 60 every time. But that runs into a couple problems, right? So one of the problems with 60 degrees over there is that A, it's less than 90, whereas it looks like it's bigger than 90, way up here. It looks bigger than 90, so that seems implausible. And also, if it's dropping by 60 every time, by the time you get to 4 dimensions, it would have 0 degrees. So that doesn't seem reasonable. So we need a different way of conjecturing. So still, we're not sure, so I'll say 60 degrees, and we cross it out, and we're still confused. So let me erase that guy. Okay, well, now you have to think a little bit more. And one way is you try to represent the problem in as natural a form as possible, as close to the way the problem actually is trying to talk to you. So here, where do these angles come from? Right? Angles are, you're going to find, in the end, you're going to find some vectors. You're going to, if you do it brute force, right, you take the dot product of these vectors, and the dot product of 2 vectors, A dot B, is going to give you the magnitude of A, the magnitude of B, times the cosine of the angle between them. Right, so now that sort of tells you that that cosines are going to actually be more important than the angle themselves. So cosine is a better representation than the angle itself. So actually, let's make another column, cos theta. Okay, so there, let me name what we just did, which is use good representations. Okay, so now the cosine, well, this one, cosine of 180 minus 1, cosine of 120 minus a half. Now we have actually a better basis for conjecturing over here. So what are some possible conjectures you could make? We're going to guess again for the cosine. Yeah? Could be minus 1/3. What else sounds reasonable? Yeah, minus 1/4. You just keep having it. Anything else? 0. Right, it just keeps dropping. You add a half each time. So now let's think about which of these seems most plausible. So 0 is a good guess, but the only problem with it is that it would suggest that in 4 dimensions, it goes from minus 1, minus a half, 0 to a half. So that would be 60 degrees. So it would be less than 90, whereas it should probably be more than 90 always. Now minus 1/4, that seems pretty reasonable. And one way to decide between these two, it's not a proof, it's a way of intuitive reasoning, is to make yet another column. So these dot products are based on how much length gets cut off. So the next thing you can ask about a triangle is, where is the centroid? So if you have a triangle, or a tetrahedron, if you have a triangle, the center of mass, which is where the carbon sits, this is in 2D here, that is 1/3 of the way from here to here. Right, so let's call this the centroid. So in 2D, this is 1/3, or let's say there's a 2-to-1 ratio between this long length and the short length. And in 1D, between the two sides of the centroid, there's a 1-to-1 ratio. And in 3D, what do you think that ratio is? 3-to-1, yeah. So that tells you there's a 1, 2, 3 over here. That sort of suggests 1, 2, 3 over there as well. So that's a plausible reason for that. It's not a proof by any means, but it's a plausible argument. So then you can just check it. Cos inverse of minus 1/3. Calculators, anyone? If you have a calculator in degrees mode, or just set it in degrees mode, because otherwise you'll have to multiply by like 57 point something. Oh, amazing. 109.47. Okay, so that's an example of solving things and getting reasonable answers without proving. And we've actually added a few more techniques. Well, being lazy, using good representations, and there's another one. When we went from 3D to 2D to 1D, what's one word you could use to characterize that process? Someone else I haven't heard. Yeah, we're making simple cases. So we're using number 2, and we're simplifying in a way that we're also being lazy. We're making easier cases, but we're also making analogies. Right? We're saying 3D is sort of like 2D. I mean, it's a different problem, but the features that we learn in 2D, we can hopefully generalize to 3D. So you're reasoning by analogy. So we're actually using simple cases, guessing, analogy, and representation and laziness all at the same time. So this is actually how problems are really solved. Nobody actually just right away writes down the theorem and everything is solved. You have to investigate, you try simple cases, you think about it, and then somehow the light dawns, you make some progress, and it's these skills that students generally don't have. They think the way you solve problems is you look in the book for the closest matching thing to the exercise that they've been given. And you want to actually try to take them away from that and try to name the techniques that are going on. Okay, so now let me give you one more example of this guy, then I'll set you off with one more problem for you guys to try. So let's revisit the odd number problem. Notice that we've used symmetry there in the odd number problem, but we can also use good representations. So let me show you another representation of the odd number problem, which is the following. And once you see this representation, you can never forget the answer. So here is 1. Here is 3. 1, 2, 3. Here is 5. 1, 2, 3, 4, 5 squares. Here is 7, right? So it's always a square, right? So that's why it's a perfect square. So once you see this representation, or maybe the symmetry argument, you can never forget it, right? So this is a good representation. So generally, graphical representations, so this includes the idea of use pictures when needed. Pictures and others. So it's not just pictures, but the idea of using pictures is because it's a good representation. It matches really well with how we think and perceive. Okay, so any questions about these techniques before you guys try a problem? Okay, so the next problem is one of my favorites, which is this one. So here's an equilateral triangle, and your goal is to bisect it, by which I mean cut its area into two equal pieces, cut it into two pieces of equal area using some curve. Like, for example, here's like that. Well, that doesn't quite bisect it, so let me erase that and do something like that. Okay, maybe that bisects it. So there's many, many curves you could make, straight lines, curves, whatever you want. And the goal is to find the shortest one. So find shortest bisecting path. Okay, and if, did anyone take real analysis as an undergraduate? Yeah? Okay, well, if you did, you might know that what the mathematicians would first do is prove that there is a shortest bisecting path before finding it. Prove that such a path exists. But we're going to just assume it exists and look for it. Okay, so that's your problem. Talk to one or two of your neighbors. If you get stuck, raise your hand, and then we'll discuss what methods you use and maybe also what the shortest path is. Yeah?
I'm not sure I understand. So
Sure.
A bisecting path starting from that cuts those two sides of it?
Oh, it can go anywhere in the triangle.
It has to be with the starting points, the starting and ending points on two sides of the triangle?
It doesn't have to, no. It might be shorter, though. Probably it's shorter to use the edges of the triangle, because if you make a purely internal path like this, then the path has to be pretty long, whereas here some of the enclosed area is given you for free. You have free sides over here. So probably it's better to do something like that than this, but you may find something that's better than anything over here. Okay, so the idea is to cut it in half by drawing some path, and if you can use the edges if you like as free, costless pieces of the path. Okay? That was a good question. It's a good conjecture. So see if you can prove that. So all the edges are the same length because it's equilateral triangle. Oh, sorry, it's an equilateral triangle in case I didn't make that clear. Any edge. Now see if you can find a shorter path, and if not, see if you can prove that. Can you think of other ones? Straight down. So is that shorter than the parallel one? You're right. The parallel one is shorter, right? The parallel one is 1 over root 2. And the straight down is root 3 over 2. Yeah, so see if there are any others. Right inside. You can calculate it, or you could try to prove that it can't be shorter or must be shorter.
Okay, so here we go. Let's test. No, we want this area. Okay, yeah. So let's the first thing is let's say we have our and we'll find the area.
Two equal areas, yeah. But it doesn't have to be a straight line. It might be a straight line, but it doesn't have to be a straight line. Right. That would be, that's definitely one path. There might be a shorter path. Some people over there suggested a line that's parallel to one of the edges. So check which one is shorter.
So we picked the two ones that and then we found the line that was root 3 across, and then we measured the area of the smaller triangle with a line that was root 3. And if this area ended up being bigger than root 3 or 2, but root 3 or 2, so it ended up being.
So if you have what you think is a shortest path, try to prove it. Prove that nothing, that's the hard part. So what path did you guys?
So like cutting off a section like
So that, right, so how long is,
another-
yeah, if this is 1, how long is that?
This is 1, root 2 over 2.
Yeah, 1 over 2, yeah.
Yeah.
Right, by similar triangles.
Right.
Right, and that's slightly better than this one, isn't it? Because that's
Right,
like .866 or something,
Right.
and that's .707. Yeah, so can you do better than that? So let me put down some of the paths that I've seen people working on. That's one, right? See if I can- Okay, so let's see if there are how many people were considering this path, even if you don't think it's the best one. Okay, so that's good. Try simple things first, right? How about this one? Slightly more complicated. Who is considering this one? Okay, a bunch of people. Any other ones people are considering? Yeah?
Around one of the vertices.
Okay, so let me draw that. So let me pick one of the vertices, say this one. So you mean something like that? Okay. Any other paths people are thinking about? All right, well, let's work out some of the lengths. Assume, let's say all the sides are 1. They're equilateral triangles. How long is this guy? Root 3 over 2. Yep. And this one? Pardon? Root 2 over 2, right, or 1 over root 2. That's right, same number. So this root 3 over 2, let's get some decimals. That is 1.732 blah, blah, blah over 2, which is 0.866. Da, da. This guy is 0.707. This one is a damn pain to evaluate, right? There's like square roots of pi's and roots and threes and God knows what else in there, and it's a real mess, and you have to actually evaluate it very closely to decide whether it's this or that, whether it beats either of these. Okay, but now, whether this guy is better than any of the others, let's leave that question aside for the moment. Suppose we find one that we think is the best. How are we going to prove it? Right? That's no laughing matter. Well, maybe it is a laughing matter, but it's no joke. Right? It's not easy to prove. So what I'm going to show you is a way, again, with a good representation and one of these techniques, where once you see it, you'll never have any doubts. Okay, so let me move this guy up. Okay, so what I'm going to do is I'm going to redraw the problem slightly. So here is the triangle we're trying to bisect. I'm going to make another copy of it. Another copy. Another copy. Another copy. So I've made 6 copies of it. And whatever bisecting path I use, I'm going to use on all of them. Okay, so now let's see what those various choices result in for bisecting paths for the entire set of 6. So first of all, before we do that, what technique am I using here? Symmetry, right? So symmetry is really, really powerful. Okay, so let's use that vertical up and down path and generalize it to here. So here is a vertical up and down path, right? It starts at one vertex, goes to the midpoint of the other side. And now let's do that again, right? So it goes from the midpoint to the vertex, and then here, here, here. Okay, so that one turns into this guy. What does this one turn into? Okay, so take 30 seconds and draw what that turns into. So this is a triangle here that it turns into within the hexagon. Okay, what does that turn into when you symmetrize? Yeah, it's a smaller hexagon. Okay, now, which guy has a smaller perimeter? This one or that one? The hexagon, right? They have the same area. How do we know? Well, they each bisected. The triangles are all bisected. So they have the same area. They're each half the area of the big hexagon. But this has only 3 sides, right? And this has 6 sides. So it's, in some sense, smoother, right? So it has a smaller perimeter. Well, going from 3 to 6, if it goes smaller, what would you like to do to make the smallest possible perimeter? How many sides? Infinite number of sides, right? So what we're doing, we're using simple cases, or in fact, I like to generalize that term to extreme cases as well. So one reason that cases can be simple is because they're extreme cases. So let me write extreme cases as well here. So an infinite number of sides is actually, in some ways, the best. Right now, what shape is the infinite number of sides? Circle, right? So how do you draw this? The circle would go somewhere like this, right? Which would produce that one, the third one. So each individual guy is bisected by a path like that, an arc of a circle. And so not only have you found the shortest path with this method, but you've shown that there can't be any shorter path, because the circle is the shape with the smallest perimeter for a given area. Okay, by this argument of extreme cases, basically. It's a famous theorem. It's called the isoparametric theorem. And I don't know when it was finally proved, maybe in the 1700s. But the intuitive reason for it is the one you just said. The more sides, the smoother. The smoother, these kinks actually add perimeter without really helping you much with area. So you take away the kinks, and you get a circle. Okay, so circle is the solution there. And when you calculate it, I think it's something like 0.69. It's slightly smaller than the straight across path, or 6.8 or something like that. But it's slightly smaller, and it is the smallest. Okay, so any questions about that? Okay, what I'd like to do now is to discuss some of the general principles behind all of this ways of teaching problem solving. So the first one is the moral, which is the following, which is that you can remember the following saying, which is a technique is a trick I use twice. So you could say when the first time you saw using simple cases, well, that's just a cheap trick. But if you use it twice, I call it a technique. And what is a method? A method is a technique you use twice. Okay, so the idea, what you want to teach your students is methods and techniques, sort of broadly defined as the same thing, so that they can use them in their own problems, because they may have completely different problems than ones that you're teaching them in class. Okay, so now how do you teach the techniques? Well, there's several things we've done. One is we've named them. If you don't name things, it's really impossible to get a handle on them. So, how to teach them? All right, so how? Okay, so naming is an extremely powerful approach, because that allows us to encapsulate the whole idea with one concept. And then every time you see that technique again, or the method again, you refine your idea of that technique, and you realize where it's useful, where it isn't useful. And by naming it for the students, you say, oh, here we use symmetry. Oh, here we use symmetry. They then start to think, oh yeah, I wonder, can I use symmetry in one of these things? They have a language for thinking about how to approach problems, which they didn't have before. Naming is so powerful that, I don't know, have people seen the movie 10 Commandments? It's the classic story of the Bible. So that my history of the Bible is a bit potted. It's from 10 Commandments slightly, but there's a famous scene in there where So Moses meets the shepherd, Jethro, I think his name is, and he thinks that the shepherd isn't one of Moses' religion, Judaism, but then the shepherd says something, and Moses says, "Oh, are you a follower of He who has no name?" So that's how they actually called Yahweh, the God of the Hebrews, was, quote, "He who has no name." Now, they didn't quite say this in Ten Commandments, but why does God go around with no name? Right? And in many, many old religions, that's true, not just in Judaism, but in the Sumerian legends and Babylonian legends, many times the gods refuse to let the mortals give them name. And in some places they actually tell you why. They say, "Oh, if you gave us names, then you would have power over us." Right? We don't want that. We don't want to give you power over us. So here we have the exact opposite problem. Right? We want to give students power over the problems that they're going to face. So we actually, and over the techniques they're going to use to solve them. So we want to actually do the opposite. Right? We want to bring the fire down from the mountain, like Prometheus did, and give it names, and differentiate it into various tools in their box that they can use no matter what they're going to do. So here are some names. You'll find actually, as you look through the chemistry problems you've solved and are going to solve, you'll see actually these come up over and over and over again. And furthermore, you'll find other techniques that I haven't listed here, and you can then name them for the students. Say, "Oh, look, here we used that one again, and then we used it again over here." Which brings me to the next point, which is another key feature is to use a diversity of examples. If you want to teach a technique or a method, you want to use a wide variety of examples that illustrate that technique, as wide a variety as possible. And I will give you a picture to show you why. So here's the picture. Okay, so now picture yourself in, again, the mind of the student. So that's a huge part of the art of teaching, is to transfer yourself into the student mind. Not where you are, but where are they? So now you're trying to teach them, say, these techniques that they're going to use over and over again. For example, symmetry in solving reaction mechanism problems, or organic synthesis, whatever it may be. But they actually, and so then you say, okay, well, I want to teach them the technique symmetry. Now, how am I going to teach them? Well, of course, I'll use an example because that makes it much more concrete. So here, you illustrate the technique with an example. Okay, so now imagine how this seems to the student, though. For you, it's really clear that this is the technique that they can use over and over again, and this is the particular illustration of it. But what does the student see here? It's sort of like on Charlie Brown, right? What did the teacher says, do this, do that, and what did the students hear? Wah, 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 wah. Right? So there's a huge communication gap. And that's exactly what happens here, is the students see this one big undifferentiated mass called the example with a bit of theory in it. And it's not clear to them which part is the general technique and which part is the example, because they don't know the technique yet. You do, so it's easy for you to split it off, but they don't. So they don't know where this boundary is. So you say, oh, okay, well, let me give them another example. Now, usually what happens, most people, for example, suppose you're trying to teach integration by parts. Well, what does the calculus textbook do? Right? It has 50 problems on integration by parts at the back, or in the end of the chapter. Right? So that's equivalent to basically doing another example like this. It's very similar to the first example. So here's example 1, here's example 2. But now look, the student has pretty much the same problem, because what they see, suppose they mentally take an overlap of the two big example technique things you've shown them. Well, the overlap is here. Right? It's still much larger than the technique itself. So what do you need to do if they're going to mentally intersect things to get them to really just have this as the remaining blob? Right? What you need to do is give them an example that's over here. Right? So this example, when it's overlapped with those, the only thing in common really is the technique. Right? So you want to illustrate the techniques with a diversity of application. And I'll just put a shorthand for that, which is this picture. Okay, so this is example 1, example 2. Okay, which is what we did here. Right? We use symmetry in very, very different ways. We use symmetry pictorially in the bisecting the triangle problem. We used it algebraically in solving the sum of the first odd numbers. So you want to use it as widely different as possible. And you could use it in a counting isomers problem and show that there's a core common idea all the way through. And then the students will pick that up much better if you do it that way. Okay, so that's two ways. And there's a third method, which is from John Wheeler. So John Wheeler was Richard Feynman's PhD advisor at Princeton. And Wheeler always said, what you need to do is you need to ask yourself the following question. So this is Wheeler's question. He said, what one or two sentences would you tell your earlier self? So yourself before you started solving the problem, that would make the solution really easy. So for example, with the triangle, maybe the one or two sentence would be, oh, look for symmetry based on the, look for a symmetry based on the fact that you can make 6 of them into a hexagon. For the sum of the first n odd numbers, again, you could say use symmetry, reduce it to solve cases, whatever the sentence is that cracks the problem. It forces you to think of that. So Wheeler's question, what would you tell your earlier self? That forces you to draw a general lesson that you can most likely use in other problems as well. Because you're forcing, if you say, well, I'm allowing myself to tell myself 30 sentences, well, that's not going to be a very general lesson. But if by forcing it to be 1 or 2 sentences, ideally 1, you're encapsulating a lesson that you can reuse over and over again. Okay, so those are the 3 core ways of making sure you're teaching general problem-solving skills, and in whatever you do. And you'll find whatever you're teaching, you'll find these techniques and other techniques come up over and over and over again, and you can use these ways to help the students learn it. Now, why does this actually work? Well, one reason is that it gives you the right kind of practice. So there's many studies on how people become experts. Why are we talking about problem solving? Well, you want students to be experts at solving problems eventually, right? You'd like them to be experts at solving chemistry problems. Well, there are many studies on how people become experts in many fields. Piano playing, concert pianists, chess grandmasters, physics problem solving. And they all the studies conclude with one happy lesson, which is that it's not based on, quote, talent. There really, as far as people can find, there's no really evidence for that talent. It's based on 10 years of the right kind of practice called deliberate practice. So deliberate practice is direct, specific feedback right away on what's going well and what's not going well. And by asking Wheeler's question, what you're doing is you're actually getting you're building in deliberate practice into the problem solving. So at the end of every problem, you're actually getting direct, specific feedback that you can use to improve your problem solving later. So let me contrast deliberate practice with not deliberate practice, just to give you an idea what it is. So non-deliberate practice is the way I learned to play chess. I just keep playing chess games. And I'm still pretty crap at chess because of that. So deliberate practice is what the chess masters do is they take a book of chess games. They look at, say, the first 10 moves of a game played by 2 grandmasters. After say 10 moves, they cover up the rest of the moves and they try to predict what they would do in that same situation. And then then they compare it with the grandmaster move. If they're the same, great. If not, they try to figure out why the grandmaster would have done that. If they still can't understand it, they look at the analysis. So then they go on to the next move and then the next move. So each time they're getting transferable lessons right away about that specific performance that they can use. And it's hours of that kind of practice that correlates with how strong a chess player people are. It's the same way if you play piano. Just playing scales up and down doesn't make you a better piano player eventually. You sort of plateau. What you have to do is take the pieces you're working on and say, oh, when I'm playing this part, my phrasing is off in this area. My fingers are stuck. These 2 fingers get stuck in this passage. I work on that, work on this little area. And integrate it up so you're actually, and sometimes you need a teacher to be able to hear what you can't hear isn't working well. So that's the role of the coach, is to guide your deliberate practice. Okay, so this is a way of building in deliberate practice, in other words, preparing future experts into all your teaching. So I wish you the best of luck in teaching the art of problem solving to your students and solving any problems that you come up with, because one of the benefits of teaching is that it helps you too. It's very much a selfish activity and an enjoyable activity. So, as I say, best wishes, and I'm happy to take any questions that you have. Questions?
So you would recommend, as far as teaching these, not to go on the first day of class and say, you know, you're going to know how to do problem solving, so I'm going to write down these 7 things on the board. You would recommend, during the course of the semester and the year, as problems come up, to say, you know, here I'm going to use symmetry to try to explain this. And then just not necessarily deliberately teach them problem solving, but kind of subversively slip it in.
Well, I think both work. Both work fine. So I actually, in IAP, I teach, and actually the Art of Approximation course I teach are deliberately structured around problem-solving techniques. So in fact, the approximation one has 8 units, and each unit is one technique. So one of the techniques is dimensional analysis, another one is extreme cases. I think, is symmetry one of them? Yeah, symmetry is one of them. So then I explicitly do it, and I think that works very well. But it also works, I don't know equally well, but it works. It's easier to incorporate into a curriculum that's already there rather than creating a brand new course as you encounter the techniques to name them. And that also presupposes the idea that well, what's going to happen as you're doing that is you're going to be actually looking for, you'll find more techniques that you didn't realize you were using. So in some ways, you can actually also ask the students to name the technique, as I asked you guys to do, and what they're doing. So you want a bit of engagement and some context for them to see that they're building up a library. So in the structure you had discussed, where it's throughout the regular semester, what you could do is just on the board, on the sideboard, so that's why I love classrooms with chalkboards everywhere, stuff that I want the students to see for the entire class or maybe the entire semester, I just write on the sideboard. Because I generally don't do derivations and long graphical analyses on the sideboard. I do them on the front board. And the sideboard, we just build up 1 or 2 words, just like over there. And then what you can do is, if you're going to push it a little farther and sort of a medium between the extreme of a whole course devoted to around the techniques versus completely regular courses, you can then, once you've seen a technique a few times, you can actually choose particular problems that illustrate that technique even farther. Okay, so basically going over to method 2 there. Other questions? Okay, well, we're right on time. So it's time for a break. Let's see, the next session is at 11? At 11. So at 11 o'clock, we'll start again sharp. But here are several resources for you, which you can collect during the break. And I guess there's food still out there, too? A little bit of food left. Okay, so there's food in the Chem Ed office. But here are some resources from the Teaching and Learning Lab. And actually, this is a bibliography I made up of my favorite works on teaching. And there's a section you'll see actually relevant to this session. There's a whole section of books on problem solving by the mathematician George Polya, who's one of the best math teachers probably of the century. And he's written classic works on problem solving, including How to Solve It, which you might have heard of. So you can take this bibliography. There's this booklet, which is if you're interested in further development of teaching skills, the Teaching and Learning Lab is offering a certificate. You can either have a non-credit certificate based on seminars on teaching and workshops, or there's several 4-credit courses at MIT, which we've listed that you might be interested in. So you can take that. It's going to, the 4 credit courses are this fall and this spring, depending on which one. And this is a guidelines on learning. What that is a bunch of sort of morals and useful advice about teaching, but rather than just being someone sounding off about their favorite ideas about teaching, it's actually ideas based on research studies on teaching. And so, for example, here's a piece of advice there, and then there's documentation to support that is given here. So you can investigate it as deeply as you want. You can just take that and use it in your classroom, or if you want to think about it more and what are the exceptions to it, there's a bunch of papers you can read. So you can take one of those, and this is the pamphlet, which is the Teaching and Learning Lab pamphlet, which if you want any further support with your teaching, you can always come to us, and this describes the services we offer. So this is actually, this whole set of material is duplicated on that table over there, so you don't have to go all crowded on one table, so parallel processing. Okay, so see everyone at 11, and we'll talk about interactive teaching.